Here is a quick run through of integration by parts. Before we get started, I want to emphasize that even though the formula for integration by parts looks cryptic and confusing, and it might seem like it can be really easy to mess it up, let me show you why that actually isn't the case. All you have to do for integration by parts, if you forget the formula, or if you just say, I don't even want to memorize a formula, I just want to know what's going on, just remember that integration by parts reverses the product rule. Okay, so here, just on a little extra piece of paper, is the product rule for differentiation in terrible notation. So there's the derivative of the product of two functions f and g, and we know that the product rule says that you just take turns with the differentiation, right? So f prime g plus f times g prime, meaning to do the derivative of f times g, well, you take the derivative of f and let g just sit there, and then you take the derivative of g and let f just sit there, and then add the two together. To get to integration by parts, just remember that integration by parts undoes the product rule. Well, how do you undo differentiation? Well, you integrate. I'm going to slap on integral signs, and this is terrible. Don't tell anybody I've done this, but I'm not going to add like a dx to the end. I don't want to clutter things up too much. We're all friends here, so it's okay if I do that, but shh, don't tell anybody important. But what we know is that the integral of a derivative will just get us back to there, up to a constant, but again, shh, don't tell anyone. The other side we don't know what to do with, but that's the whole point. This is integration by parts. It's just written in a way that you're not used to seeing it. If I, for example, solve for this particular term, what I'm going to do is keep it by itself and then collect all the other terms on the other side of the equal sign. So remember, we started with the product rule for differentiation, found the antiderivative of the whole thing to reverse it, allowed the antiderivative of the derivative just to go back to the original function, and then we said, hey, this looks like a good integral for whatever reason, let's solve for that. And boom, now we have integration by parts. Integration by parts just tells you that if you're facing an integral or an antiderivative that looks particularly nasty, you can consider the strategy of exchanging one of the pieces of the product in your integral for its derivative. The price of that is that you also have to exchange the other part for its antiderivative. And so in this version of the integration by parts, look what happens. Here's an integral of f prime of something we're going to call f prime times g. We're going to convert that into this expression over here, which is still an integral, but g has been replaced by g prime. In other words, g has got knocked down a peg by one level of differentiation. So we're looking at this particular problem, and we say, this integral would be better if I could trade g for g prime, and then I could solve it in this form instead. But again, remember, the price for that is having to swap also f prime up to f. Okay? So that's integration by parts. It allows you to exchange one integral for a second integral where one of the pieces is swapped out for its derivative at the price of exchanging the other part for its antiderivative. But that can be strategic. So consider this one. Imagine taking this integral, which is a product of this integrand, which is the product of x squared and cosine. We don't know how to do the integral currently, but just consider, would it be easier if I could swap out cosine for its derivative and create a new integral in that form? Well, if I swapped out a cosine for its derivative, I would be exchanging a cosine for a negative sign. That doesn't really help things, right? Sine versus cosine, one's not easier than the other to deal with. And the price of that exchange would be to come over to this part, the x squared, and swap it for its antiderivative. So if we said, I'm going to trade out cosine for its derivative, the price for that is to trade out this piece, x squared, for its antiderivative. That's actually going to make the integral worse, because we will be introducing a sine and an x cubed. Ugh, bad idea. But let's try thinking about it the other way. Let's say, and I'm just going to write it down here. Okay, here's a version of integration by parts that just says, look, we're going to match format, and we're going to call one of these two things x squared or cosine x, f, and we're going to call one of these two things g prime, and we're going to reconstruct the integral we have in terms of a new integral where one of the parts, in this case f, got traded for its derivative f prime, and the other part, which is g prime notationally, got traded for its antiderivative g. In this case, it will be strategic to allow x squared to be associated with f. So if we let f be x squared, that means that the new integral we're about to construct will actually have 2x dx in its place. The price of that is to swap g prime for g, in other words, to swap g prime being cosine of x for g being sine of x. This antiderivative does have a constant hiding in the background, but it's just going to get rolled into the big arbitrary constant that we put onto the end of this whole integral anyway, so we don't need to clutter things up right now. With these assignments made, that tells us that the integral of x squared times cosine of x dx can be reconstructed as f times g, x squared times sine of x, minus the antiderivative of f prime, 2x times g, and this dx that's part of f prime, I'm going to push it out to the end there. Okay. Note that when I was making these assignments, anything that was a derivative had the dx part stuck to it. Here we created one. Here we took the dx and put it there. Everything looks good. The notation is right. Maybe a little tidying up. And so the integral, the antiderivative of x squared times cosine x, can be reconstructed using an integral antiderivative with x times sine of x. So we've made it one step easier. Now, we still don't know how to solve this immediately, but we've gone from x squared times a trig function, and we've knocked it down a peg to x times a trig function. So just consider this a brand new problem, and do integration by parts again. I'm going to try some different letters here to emphasize that, well, since f and g have already been used, I don't want to reassign them, and to emphasize that the notation doesn't matter. All we need to know is that we're going to pick one part of this integral to be something that's going to be exchanged for its derivative, and that leaves the other part to be exchanged for its antiderivative. And just like the strategy above, here with x times sine of x, it's not advantageous to trade sine out for its derivative. That just changes sine to cosine. And the partner move to that would be x would get exchanged for x squared, so that's no good. So let's let the piece we're going to swap out for its derivative be x, which leaves everything else as the piece that's about to be swapped out for its antiderivative. If u is x, u prime is just dx. And if v prime is sine of x, then v is negative cosine of x. And again, plus c, but that'll wait. So if we carry this down, integration by parts says, now I'm going to consider a version of this written out with u and v prime rather than f and g. So this integral right here, say the integral of u times v prime, will be u times v, so this times that, and I'm arranging the minus sign strategically, minus the integral of u prime v, or this times this, so minus the integral of negative cosine x dx. So uv minus the integral of u prime v. Clean up. Double minus sign. Double minus sign again. Ooh, no, triple minus sign. Look at that. One of them, two of them, whoops, one right here, and one right there. So these two minus signs will make a plus, but that minus sign leaves everything as minus. There's the 2 and cosine x dx. And so what we've done here is we've started with an integral that's x squared times cosine of x. One round through integration by parts allows us to trade out x squared for its derivative, 2x, in a newly reconstructed integral. That knocks the complication of the integral down a peg. This one still can't be done immediately, but we just run through integration by parts again. We reconstruct this integral with an expression where the new integral has x replaced by its derivative at the price of having sine of x replaced by its antiderivative, but that led us to this integral and this other clutter. And everything is rolling together all the way through, and we get down to this mess. Now this takes one more step, right? This integral right here, which I've run out of room for, that will be a sine of x, right? And then there's going to be a big plus c stuck onto the end of everything. I will leave it to you to do that cleanup. I just wanted to go through the motions of the strategies through integration by parts.